Statistics is a part of everyday life. We can use it when it comes to finding the average height of teenagers, creating a sampling distribution of free throw averages, or finding the probability of people using water cups to drink soda. But stats can be misleading. So why does this happen? Just look at what happened at UC Berkeley in 1973. The university was sued for having a gender gap in admissions. Students cited a statistic that said that 44% of admits were men, while a meager 35% of admits were women. UC Berkeley reacted by looking at each department separately, and here's the data table they found. Okay, it looks like men are admitted at a higher rate than women. Okay, but now we'll separate the data by department. Here's the new data table. Wait, it looks like women are admitted at a higher rate than men in some of these circled spots. Confusing, right? Well, it all comes down to the pooling the university did. Since more women applied to and were accepted by departments like law and medicine, which had smaller number of applicants to begin with, their overall numbers were lower. On the other hand, men applied to science departments that had much higher admit rates. So, in the end, the general claim about a gender gap was not justified and the paradox was resolved. Okay, so why does this occur? Well, the reason this occurs is because there is something called a lurking variable, and in this case, it's the department in the college. This phenomenon is called Simpson's paradox. Wait, Simpson like Homer Simpson? No. Simpson like your neighbor, Mr. Simpson? No, not him either. This is Edward H. Simpson, a British statistician who first described this phenomenon in 1951. Every Simpson's paradox involves at least three variables: the response, the explanatory, and the lurking variables. Here's another example. Say you decide to spend your summer figuring out if people like lemonade or soda better. Since your parents drag you along on a vacation to your family's cabin in rural Wyoming, you can spend the long hours talking to both the locals and the visitors like yourself. While you're serving the drinks, you ask each customer where they're from and make notes about them in your notebook. Here's the table you construct. Okay, so it looks like women are 10% more likely to drink lemonade than men are. Now you decide to combine the data from the rural folk and the city dwellers. Wait a minute, something changed. It looks like according to this data, females are about 14% less likely to drink lemonade than males. Why? Well, it's because of Simpson's paradox. But how do we know which set of data is correct? Well, since the first table accounted for location, the working variable, this data is correct. In this example, there are two surgeons, surgeon 1 and surgeon 2. Surgeon 1 treats 100 patients and 95 survive, while surgeon 2 treats 80 patients and 72 survive. Well, which surgeon should we choose? Surgeon 1 seems like the better option, right? Now when we combine data, surgeon 1's patients had a 96% survival rate, while surgeon 2's patients had a 97.5% survival rate. This is because there's a lurking variable. A lurking variable is the difficulty of surgery in this case. So, surgeon 2 is better. In conclusion, Simpson's paradox tells us to check where the data comes from, how it was obtained, what it's really saying, and if there are any lurking variables. The end.